Good evening, everyone. Welcome to Unacademy. Welcome to the session. This is Yoshinga sir. So let me start the session, or let me start the new topic in this Learn Digital in 20 hours. As we promised, I'm going to complete the digital circuits in 20 hours without any interruption. On the promised date, that is, I promise you that I will be completing the syllabus by this end. In the first class, I taught you that maybe maximum 25th तक मैं plan कर रहा हूँ to complete. That is by tomorrow. Mostly the syllabus will be completed. Maybe extra today and tomorrow. 99.9% if there were no interruptions, most possibly it will be completed. Okay, so today the last chapter of the digital circuits we are going to start, that is data converters. That is how a circuit of digital data to be converting into analog format, how to convert analog format data into a digital. All these things we will be discussing today. So let's start the session. So the new batch is going to start on 28th Jan. If you want to take the subscription, you can take the subscription for 24 and 25. Okay. In this batch already, the presently I have started signals and system on Jan 18th, and it is going on in the morning 7 a.m. And the new subject is going to start today, 28th. That is on evening 5 p.m. by Sujay sir, and also orientation session will be started by our Umesh Dande sir. So this batch will be having many advantages like top educator का classes मिलेगा आपको. You can access both the live as well as recorded classes, doubt solving sessions daily, and DPP मिलेगा आपको, daily practice set, and सभी PYQs and many practice questions will be added in your session. So this is the batch for IRMS also. So for IRMS batch also, you can, we will be starting for CSC mains, IRMS, GATE, and ESE, for all of them single batch. So there is an offer running on right now, that is with the Unacademy. You can get up to 30% off by taking the subscription using my code Shankar10. Take the subscription using my code. You will be getting the maximum benefit using the code Shankar10. Including the price raise, you almost save 27% on your subscription price. Okay, the prices may increase soon. Before that, take the advantage. Right, so let's start. So the next topic we are going to discuss is data converters. How to convert the data in one format into another format. Suppose you take any system. Most of the systems आजकल हम तो use कर रहे हैं ना, वो तो digital systems है. उसको data चाहिए, digital data to process the data. Signal processing के लिए, digital signal processing के लिए आपको digital data चाहिए. But input जो होता है ना, हमेशा जो नेचर पे आपको मिलेगा वो तो एनालॉग इन नेचर. मैं तो बात कर रहा हूँ अभी. ओके, मेरा माइक तो कैप्चर कर रहा है. What I am speaking is analog signal, mic capturing, and it converts this into electrical signal, which is an analog signal. Then in the system, it will be converted into a digital format. Then it will process the signal like amplifying, eliminating the noise, many other things. And then it gives the output again in the analog format by converting the digital into analog. So in day-to-day life, there is a need, you need to convert the analog signal into digital or digital signal into analog. For example, you are measuring the temperature. There is a detector which can detect the temperature, give you the electrical signal. Then that electrical signal is processed, and while giving the output, while processing, I may be converting this analog into digital and process. But while giving the output, suppose 24 degrees is there. If I give 110000, that doesn't make sense. You should convert into a proper format and give, then only end user can understand. So to display the result, you should again convert this into analog format. It is maybe as simple as binary to digital, or sometimes it need not be binary to digital every time, binary to decimal every time. It is some continuous form to digital format. So you can see here, you have an analog signal, microphone is there. There I have taken ADC, which converts into a digital signal. Okay. Discrete signal means first we sample the signal. Then we quantize this magnitude to the nearest possible binary level or digital level. Then it is called as quantization. Then it will convert the digital signal, analog signal into digital. You can sample it, it becomes a discrete signal. After that sampling, that is time domain, it will become discrete. In magnitude also, if you make it discrete by reading the signal and give it or assigning it to the nearest possible digital value to this, then it is called a digital signal. So we give it to a system for processing or for doing some manipulation. Iske baad, while giving the end user response again, I need to use another DAC. As simple as this. So this is required in your day-to-day life. So we start studying DAC and ADC. First we start with specifications of the DAC. Okay, we start with the specifications. First we will be discussing DAC, then we will move to ADC also. Okay, chalo. Let's start with the specifications. Before that, let me draw one input. See, this is my digital input. Okay, this is my digital input, and here I am measuring my analog output. For example, okay, so when the input is starts with 0 0 0, then 0 0 1, 0 1 0, 0 1 1, 1 double 0. Suppose this is my input. Okay, so I have 3-bit input, digital input. I want to convert into analog output. Okay. So for input equal to 0 0 0, you got the output is 0 0 volts. So when input is 0 0 1, you got the output, it is equal to 0.5 volts. Next, for some other input, you got the output is equal to 1 volt. So with the given input is increasing, my output is also increasing, for example. Okay, see here. And you are getting the output equal to like this. For different inputs, you are getting the different output. Okay. So the output will be here, say 0.5 volt, 1 volt, 1.5 volt, 2 volts, 2.5, 3, and here. So this is how you are getting the output with respect to input. For example, in a particular system, say for 1 bit change in the input, your output is also responding linearly. This is the meaning of the here you draw this line. It is a linear system. Yes or no? This is the important thing. The response must be linear. For equal increments in the input, there must be equal increments in the output. Okay, so now listen here carefully. Now here, so for 1 bit change in the input, what is the change in the corresponding change in the output? For every 1 bit change in the input, my output is changing. Output is changing by how much voltage here is given by step size 0.5. It is also called as the resolution. It is also called as the output when one LSB is equal to 1, remaining all inputs are 0. What is that value? What is that value? 0.5. Between 2, what is this? This is called step size. Step size is equal to resolution is equal to step size is equal to resolution is equal to 1 LSB. That is given by here the maximum output you get is 3.5. Now that is taken as V reference by number of steps. It is also given as V reference by 2 power n minus 1 if the input is binary. If the input is binary, we can say it is equal to V reference 3.5 by 2 power 3 minus 1, that is 7.5 is the answer in this particular case. For example, now see. Suppose it is here for every bit, if it is changing by 1 volt, 1 volt, 3 volt, 4 volt, 5 volt, 6 volts, 7 volts. So step size here will be how much? 1. So for 1 bit change, what is the corresponding change in the output is given by the resolution. If resolution both come hua to, I can represent my given input more accurately. That's why when you take a television, you ask high resolution television, because available image go, it will make it into n number of parts, the screen size go. If you make more number of parts, you can represent more accurately. How, sir? For example, if it is the resolution here is 1 volt now, what is the disadvantage? When the input is in the range of 0 to 1 volt, it will represent as 1 only. 1 to 2, it will represent as 2. So 1.2, 1.3, 1.4, 1.5, 1.6, 1.7. Maybe you may use different type. Where I 0.5 to 1.5, I may represent as 1. What, that is a different case. But see here. So suppose your input is 1.7. I represent as a 2. 0.3 error will come. Yes or no? Like that, maximum error will come when the size difference gap is maximum. I mean, I cannot represent here 1.2, 1.3, 1.5. I can represent 1 and 2 only. Between signals are always represented either as 1 or 2. So there is a possibility of losing, I mean, accuracy. So similarly, if the step size is 0.2, suppose you get 1.7, maybe I represent as 1.8 equivalent, 1.8 ka digital equivalent. and while converting I'll get back my 1.8. So difference is less, so I can represent more accurately. So depending on the requirement, we may increase the number of bits and we make it more accurate. If you increase the number of bits, the available range can be made into more number of parts. Then I can represent my signal. While reproduction, you get more accurate signal. Let's continue, just a minute. Right. So that is about the basic of the resolution. Let's start the definition of the resolution. So resolution is given by it is the change in the analog output corresponding to one bit change in the digital input. If the input is changed by one bit, the output change is given by resolution. It is also defined as a step size or LSB. It is the output when all the bits are 0 except LSB. So the resolution is given by V reference by 2 to the power of n minus 1. Okay, it is also given by, I told you, number of steps. It is equal to V reference by 2 power n minus 1. Approximately 2 power n भी ले सकते, but the accurate answer to 2 power n minus 1. ठीक है, this is the formula for resolution. Now let's move for the next. Analog output. कोई भी input आपने दिया तो the output you are getting. The output you get for any analog input is given by the analog output. The formula here is resolution into the decimal equivalent of the binary input. So V reference by 2 power n minus 1 into the decimal equivalent of the input will give me the resolution. Give me the resolution, right? So let's move for the next one. There is another formula called full scale output. Full scale output is given by output corresponding to maximum digital input. We should learn specifications compulsory, because to select any EDC or DAC, we should know its specifications. So if you take here, the maximum input is 2 power n minus 1. So the full scale output FSO equal to resolution V reference by 2 power n minus 1 into 2 power n minus 1. That's V reference. That is the full scale output. Okay. So nothing but V reference and full scale output more or less same until specified specifically by the examiner. So percentage resolution is given by how much percent resolution is with respect to V reference. What is the formula for resolution? V reference by 2 power n minus 1 by V reference into 100%. That is 1 by 2 power n minus 1 into 100%. Okay, that is percentage resolution. Next, accuracy. So हम तो जो expect करते ना इसमें, because of the resistances, tolerance, whatever may be, there will be some deviation compared to the expected value. The difference between the measured value and expected value will give you the accuracy. Okay, it is always specified in our DAC and ADC with respect to full scale output, maximum output. Say for example, you take a DAC is having a reference voltage of 15, accuracy is 0.2%. For input of 1010, what is the corresponding output? Firstly, what is accuracy? 0.2% of, always we should take with respect to full scale. Okay, we should speak with respect to full scale. So 0.2% of 15, that is 0.2 into 15 by 100, that will give you 0.03 volts. So for a 4-bit DAC, n equal to 4, what is the resolution? V reference by 2 power 4 minus 1 1 volt. Okay, so if the input is equal to 1010, what is the decimal equivalent of 1010? 10. What is the decimal equivalent of 1010? 10. So the output expected is resolution into decimal equivalent, that is resolution is 1, decimal equivalent is 10, you are expecting 10 volts, but what you will be getting it is the output will be 10 volts plus or minus 0.0. So it might be in the range of 9.97 to 10.03, right? So this is the expected output, sorry, this is the measured output due to the accuracy. So 0.2% of full scale will be deviated for every input. Don't take 0.2 square 2% of that particular input. Okay. And this is the full scale output. Right. Let's move for the next. So linearity, for equal increments of in input, output must also vary linearly. This is the required condition for any DAC. It is very important for a DAC to work properly. It doesn't mean the input and output should be value same. Output and input must be linearly related. When input is doubled, output must double. Input is half, output also half. That is how a DAC should be properly designed. And monotonicity is a part of linearity only. Output should be a linearly related to the input, and the settling time is the time required to settle. Suppose you have given input, it requires some time to read the input. You have given the output also requires some time to get it as a valid value because of the capacitances involved. So to get plus or minus half LSB of the final value, how much time you need is called as a settling time. So, right, that will finish the ADC and DAC specifications, right? So, we can do a question, I think. Yeah. So, this is the question given in GATE 2020. You have a 10-bit DAC is calibrated over the full range of 0 to 10 volts. If the input to the DAC is 13A, what will be the output? You can try. Okay. Okay. So, here n equal to 10. Okay, V reference is also equal to 10. Resolution is equal to 10 by 2 to the power of 10 minus 1, 10 by 1023. Right. Now the input is how much? 13A, that is 16 square plus 3 into 16 plus 10. decimal equivalent 16 power 1, 16 power 8 is 10. So this will be 256 plus 48 plus 10, 314 I feel. Okay, so the what is the output? Output equal to 314 into 10 by 1023. Let me do the calculation. So it will be count to be 3069, 3.069, approximately 3.07. Option B is the right answer. Okay, so now we will start the data converters. The first one we are going to discuss is weighted resistor type DAC. Then we will discuss R2R type DAC, then R2R type voltage switched, current switched. Those things we will be discussing. Then we will do the necessary problems that will finish the DAC part. Then we will go for the ADC. Okay, so let's continue that. DAC. In the DAC, we are going to discuss regarding different types of DAC. The first one we are going to discuss is weighted resistor type DAC. Okay, then R2R ladder type DAC. In that again, voltage switched and also current switched. These are the different type of DACs we are going to discuss in this right today. So we'll complete this part at least today. So let's start with the R2R type weighted resistor type DAC. But before that, you must have the basics of the op amp. I hope you know the basics of the op amp. Just a minute. Chalo. So now let's start that. Weighted resistor type DAC, D2A converters. Firstly, let me draw the figure, then I'll do the explanation. So this is simply as simple as this circuit is working like a weighted resistor type DAC. Here we add the resistors in the terms of weights like R, 2R, 4R, 8R, 16R and so on. So the first one here will be this one acts like a MSB and this one works like a LSB. The first one will be working like MSB and the bit which is the resistor which is close to the this one क्या बोलते हैं op amp will be working like MSB of your input and LSB of the input is the last one. Okay. So here how a particular bit is given is like this. You have a D3 for example, or you take any bit DI. That particular bit is just like a switch which connects to two voltage levels, either 0 volts or maybe some voltage called VR. VR is not V reference. VR is the voltage when input is equal to 1. This is not V reference. V reference अलग बात है. So it depends on the particular bit. A particular bit 1 है तो it will give VR. 0 है तो it will connect to 0 volts. So like this, bit 1 and bit is 0, you will connect to two different voltages. So here a particular bit is 1, I give some voltage, particular bit is 0, I'll get some other voltage. So how to prove this is working like a DAC means write the output equation. Output equation तो हम कंपेयर करना चाहिए स्टैंडर्ड डीएसी का इक्वेशन. व्हाट इज द स्टैंडर्ड डीएसी का इक्वेशन? रेजोल्यूशन इनटू डेसिमल इक्विवेलेंट. सो फाइंड द आउटपुट एंड चेक विथ रेजोल्यूशन इनटू डेसिमल इक्विवेलेंट. सो व्हाट इज योर आउटपुट हियर? It is a summing amplifier circuit minus RF by R into D3 plus RF by 2R into D2 plus RF by 4R into D1 RF by 8R into D0. Here you take minus RF by 8R common. It will give you 8D3 plus 4D2 plus 2D1 plus D0. Okay sir, fine, it is clear. Now listen carefully. Here I can say any particular bit di is equal to simply di into VR. If the particular bit is 1, you get VR volts. If the particular bit is 0, you get 0 volts. So I can say this is minus RF by 8R into 8 into VR into B3, 4 VR into B2 plus 2 VR into B1 plus VR into V0. You can take the VR common. Minus VR by 8 into RF by R into 8B3 plus 4B2 plus 2B1 plus B0. Okay. Right. So here, just for the sake of mathematical convenience, I multiply with 15, divide with 15. Is there any issue? No, sir, because 15 by 15 will give you 1 only, into minus VR by 8 into RF by R into what is this 8B3 plus 2B2 plus 4B2 plus 2B1 plus B0. It can be integral sum of I equal to 0 to 3 2 to the power of I BI. Right. So here small condition. If you take this part and replace with V reference, this 15 can be written as 2 to the power of 4 minus 1 into, now listen here. Now what is this? This is nothing but the decimal equivalent of the number. Sigma I equal to 0 to 2 to the power of I equal to 3, 0 to 3, 2 to the power of I BI. It is nothing but the decimal equivalent of the binary number. And V reference by 2 power n minus 1 can be written as resolution into decimal equivalent. So it is satisfying the required condition. My output must be equal to resolution into decimal equivalent. So it is satisfying the condition, output is equal to resolution into decimal equivalent. Why I have taken this part as V reference? What is V reference here taken is minus 15 by 8 VR into RF by R. Sir, shall I remember this, sir? No need to remember anything. But आपको समझ होना चाहिए why I multiplied 15 by 15 and so on, because what is the meaning of V reference is, V reference is when all the bits are 1, whatever the maximum input you can apply is all the bits are 1. When all the bits are 1, whatever the output you get is called as V reference. Suppose you substitute here all ones, B3, B2, B1, B0 सभी 1 substitute करो, what do you get? 8 plus 4 plus 2 plus 1 is 15. So minus 15 by 8 VR into RF by R. That is the V reference. That is the reason here we multiplied with 15 and divide with 15 to show that this part is equivalent to V. Here this coefficient may, I want to write it with respect to V reference. That's why I multiplied with 15, divide with 15, or 2 power n minus 1, 2 power n minus 1. Is it clear? Without this manipulation, simply substitute all ones. Whatever you get here, that is nothing but your V reference. Okay, V reference is the output you get for the maximum input. So no need to remember anything in this equation, guys. सिंपल सी बात तो ये होता है, द गेन आर एफ माइनस आर एफ बाई आर इंटू, ओके, वट एवर यू अप्लाई हियर दैट विल बी बाई 2 हो जाएगा, ये तो बाई 4 हो जाएगा, ये बाई 8 हो जाएगा, ये बाई 16 हो जाएगा. दैट वी विल डिस्कस इट एनीवे, डोंट वरी. नाउ लेट्स मूव फॉर द नेक्स्ट. Almost, I mean here just remember this. Okay, remember this one, that is sufficient. RF by R into the input you applied, RF by 2R into input you applied. This is easy to remember, no need to remember all this. This is for your understanding that it is working like a R2R, sorry, weighted resistor type DAC. बट इस सर्क्यूट में कुछ दिक्कत तो है. क्या दिक्कत है सर? ये वाला सर्क्यूट में दिक्कत क्या है सर? Here you should have, you need to get wide range of resistors, wide spread of resistors बोलते हैं. R, 2R, 4R, 8R. If you take more number of bits, 16R, 32R, 64R, 128R, 256R. So exact multiples मिलना थोड़ा सा मुश्किल है, क्योंकि हर रेजिस्टर को थोड़ा सा रेजिस्टेंस तो टॉलरेंस तो होता है. Whatever you take the resistance, it will be having some tolerance. It will be having some plus or minus maximum 20% that vary हो सकते, depends on the resistor you have taken, and all the resistor values are not physically available. Out of first 100 values, exactly 31 different values are available in the resistor. So exact multiples मिल सकते, नहीं मिल सकते. Maybe we use variable resistors and make it also. Okay, but so you acquire wide range of resistor is one disadvantage here. So generally it is limited to less number of bits. And second disadvantage here, compared to the other types, it requires less number of resistors, but spread range of resistors is more. Next, the disadvantage, one more disadvantage here is different inputs will give different input resistance. If you connect this, it is input resistance is different. If you connect this, different input resistance. Even its step size may not be uniform, depends on the tolerance of the resistance. Because of all these factors, we move for R to R type of DAC, where we don't use these many different type of resistors. We use only two type of resistors, R and 2R. Okay, so I've given all these possible points. The disadvantage of with the weighted resistor type DAC is it needs wide range of resistors from R to 2 power n minus 1 R. So here the last bit will be 2 power n minus 1. So it is difficult to get exact multiples of R. So we confine to less number of bits only. Okay. So come number of bits may we will be limiting this. Its input impedance is not fixed due to the tolerance of the resistors. Its accuracy is less and maybe may not have uniform step size. We can overcome सभी disadvantage जो है ना, इसको overcome कर सकते हैं by using R2R type of ladder type of DAC, which we are going to discuss now. Okay, only two type of resistors are used, R and 2R. So let's start. Okay, इसमें first we are discussing voltage switching. Then we discuss current switched, then we do the problems and we can end the class. Okay? Takes time, don't worry. Don't be excited. We are taking the example of the 4-bit DAC. Here we apply the bit 3, 2, 1, 0. Okay. A particular bit is 1 or 0, you will be giving the volt. See here, don't, I mean previous case also. I am not showing the switches, but you assume that we are connecting between two different switches or two different voltages when a particular bit is 1 or 0. Okay, so this is what we call R2R ladder type of DAC, where here I am using only two type of resistors, 2R and R only. But whether it will work or not, we will see. But we require more number of resistors here compared to previous case. That is true. Okay. So here please remember one more thing. Here whatever we applied, this VR is the input you are applying when a particular bit is 1. V reference is the output of, that is the maximum when in output, when all input bits are equal to 1. Okay, when sare input bits the 1 हुआ तो then what is the output you get is this one. Okay, चलो. So let's discuss this. ये discussion करने के पहले here this is my V naught. Let's take this as Vx. What is your V naught? 1 plus R2 by R1 into Vx. This is the condition. So all you need to do is find the Vx. Ideal op amp में input current तो 0 है भाई, ठीक है. So this is a non-inverting amplifier. Output equation is equal to 1 plus R2 by R1 is the gain into this Vx. I hope you know the basics of the op amp, so that's why I have not revised them, because anyway it is a, this is a what we call crash course. Right. So now, before going further, let me give you one basic of the network analysis. Network analysis का एक basic देना चाहिए मैंने. So what is that, sir? Listen. If you have a resistor, voltage source V parallel with VR, you can apply Thevenin's theorem or source transformation. This will be equal to R by 2 series with V by 2. Is it okay? The same way, suppose if you have R V by 2 and R or 2R ले लो दोनों. What is the equivalent is? You get here R and this V by 2 will become V by 4. This is the basic, equivalents which we study generally in the source transformation of the network analysis or Thevenin's equivalents. So whenever you have a voltage source series with a resistance parallel with the same value resistance, equivalent is simply that voltage by 2 series with resistance whatever you have by 2. Okay, now let's find the output equation of the circuit which we have. Now suppose here if only V3 is equal to 1 and other bits equal to 0. So when V3 is 1, we connect the voltage VR into V3 or only V3 applied, you say. Only V3 applied but remaining bits are zeros. So the remaining bits you permanently ground it. This is not a bit, this is always ground. Okay. In this case, what is the Vx? You will be getting it. So let's find it. Here, ये बोल रहा हूँ मैंने, here V3 1 है तो VR आएगा, V3 0 है तो 0 volts मिलेगा, इसलिए VR into V3 is the equation. Only V3 applied, remaining other bits तो 0. Now आप ही बताओ 2R parallel with 2R, R होता है, R series with R, 2R parallel with 2R, R because they are grounded ना. 2R series, 2R parallel with 2R, R, this is R, series with R, 2R, parallel with 2R, R, series with R, 2R, parallel with 2R, R, series with R, 2R. So the equivalent here is, what is the equivalent you will be getting here? Two R is the equivalent in series with 2R and the voltage source value VR into V3. Okay, this is where you are measuring your Vx3. So as per our just discussion, op-amp ka input current kitna? 0. So voltage source series with resistance parallel with resistance, what is the equivalent? VR by 2 and V by 2. So here, what is your Vx3? Because this current 0, there is no drop in the resistor, this voltage will come as usual. That is VR V3 by 2. So my Vx3 equal to VR V3 by 2. ठीक है, my Vx3 equal to VR V3 by 2. So let's move further. Similarly, if only V0 is applied, V2 is applied, what happens? Then we can conclude. If only V2 applied, इस केस में क्या होता है सर? Let's find the response. Okay, here इसको ग्राउंड करो, इसको भी ग्राउंड करो, ये भी ग्राउंड करो, बट V2 पे you should connect VR V3 नहीं V2, that particular bit V2. Here also you see this part is 2R parallel with 2R, R series with R, 2R parallel with 2R, R series with R is 2R. So the equivalent here will be, this part will be 2R and 2R and this will be VR into V2. And here you have R and 2R. This is where we are finding the Vx2, that is Vx when B2 is applied. Now again, what is the shortcut? If you have this part, voltage source series with resistance parallel with the same equivalent, so R by 2, that is 2R is divided by 2, series with VR into B2 by 2. The remaining part you connect as it is. The remaining part you connect as it is. What is the remaining part here? R and 2R. So this is your Vx2. So this will be again total how much? 2R na? So 2R parallel with 2R. I mean VR voltage source series with resistance parallel with the same resistance. So this will be again R and this will be VR B2 by 4. So you can see here, op amp में कोई current नहीं चलेगा. Vx2 equal to, there is no drop here, VR B2 by 4. Now we can conclude. Because here up to this it is fine, right? Now we can conclude like this. If only V3 applied, VA3 equal to VR into B3 by 2. VA, okay, then similarly we also find only B2 applied, VA2 equal to VR B2 by 4. Then I can say if only, then based on this, similarly I can say when only B1 is applied, केवल और केवल आपने B1 अप्लाई किया तो आपका VA1 क्या होता है सर? VR into B1 by 8. And only B0 applied किया तो VA not equal to VR into B0 by 16. So what is your V9, VA or VX, whatever, X. What is your Vx in then? VR B3 by 2, VR B3 by B2 by 4, VR into B1 by 8. This is all derivation, no need to remember, but that is for our satisfaction that we want to prove that it is working like a DAC. ठीक है, इसलिए. So what is your V0? 1 plus R2 by R1 into this part Vx. What is Vx? VR upon 2B3 plus VR upon B2, VR upon 4B2, VR upon 8B1, VR upon 16B0. So here 1 plus R2 by R1 into, you take the 16 LCM, 16 into VR by 16, you take common, 8B3 plus 4B2 plus 2B1 plus B0. So here you divide 15 with 15. Sigma equal to 0 to 3, 2 to the power of I, Vi. Here 0 to 4 are. Okay, again the same story. This part I replace with V reference. V reference upon 2 to the power of 4 minus 1 into the decimal equivalent. So again you are getting resolution into decimal. Here what is V reference? It is not same as previous case. 15 by 16 into 1 plus R2 by R1 into VR. How to decide what is your V reference? Just substitute all ones in this equation. Whatever you get, that is your what we call V reference. That will give you 15 by 16. When you substitute all ones here, 15 by 16, this one is the V reference. VR is the voltage you applied when a particular bit equal to 1. Don't confuse between the two. and here also resolution into decimal equivalent, but I have used only two type of resistors. Okay, and here one more thing, don't remember all this equation. ये सभी equation याद करना नहीं चाहिए, केवल और केवल if you remember what we call simplest way to find the answer is I will show you. Okay, let me take one question for you. Suppose what is V naught? How to find it? What is, suppose this is the circuit or this is the question given. R value दिया, R1, R2, R2, R1 values तो दिया, R value भी given. For example, what is your V naught? Very simple. Don't worry about the entire formula we discussed. V naught is equal to, what is your V naught? V naught equal to simple 1 plus R2 by R1 15 by 1 into whatever you apply that by 2, whatever you apply that by 4, the next input by 8, the next input by 16. It can be 1 volt, 5 volt, whatever you have, apply that. If it is 10 volt, keep 10 volt, minus 5, keep minus 5. So what is the answer? 16 times 1 by 2 plus 1 by 16. What is the answer you will be getting is 5 volts. Suppose if input is made 1010, its equivalent in the binary is 10. If your input is made 0101, check it at home. You get 0101 means binary input of 0101, decimal equivalent is 5. If input is made 10, you got say 5 volts. If input is made 5, that is 0101, you should get half of the previous. Half of this will be 2.5. You check it. If suppose 0101 is applied here, what happens? Here 1 need not be 1 volt, it can be any voltage, you should substitute that particular. This is the simplest way to find the output equation. Gain into this by 2, this by 4, this by 8, this by 16. Bas ho gaya. Whatever nearest to the op amp should be MSB by 2, by 4, by 8, by 16. So the same circuit can be asked. They have asked also in one of the GATE paper. I have discussed the same thing before last year or last year also with inverting amplifier, which nobody discussed, but the same thing appeared in 2022 question paper. Let's do that model also. You can see my 2020 videos which are available in the YouTube on this topic. I have done that. Chalo, the same question. Okay, so now see here, you need to find, you want to find what is the V naught. Say apply this 5 volt, this is ground, and this is again 5 volts. What is the V naught? So I can say my V naught is equal to whatever may be minus RF by R equivalent into 5 by 2 plus 0 by 4, 0 by 8, 5 by 16. But what about this RF here? 1k. What is the R equivalent you should take? Don't blindly apply the formula like previous case 1 plus R2 by R1. Here what is the R equivalent is? Don't blindly say sir R equivalent maybe 1k sir. No, you should apply one input and cross check it better always. So here if only B3 applied, okay, in that case what happens? Yes, abhi equivalent to 2k na, and this will be 2k and 5 volts. This will give me 1k and 5 volts, and the remaining part of the network is 2k. What is your V naught here? Minus 1k by V naught of 3. 2k plus 1k. This is what the R equivalent. So here 2k plus 1k into 5 by 2. Be careful. Okay. So if this is not given, maybe it is okay. This is optional. Examiner may give, may not give. To confuse you, he may insert this. Okay. If he has not given, okay, it is a 1k by the total equivalent be another 1k. There is no issue here. But if this is given, you should be careful. Check for at least one input. What is the input resistance coming here? What is the equivalent resistance coming here? That by this you should take it from the op amp basics. So if they have not given, there is no issue. दिया तो या ध्यान देना चाहिए कंपलसरी. चलो लेट्स मूव फॉर द नेक्स्ट. Right. So what is the disadvantage with this voltage switched R to R type DAC is every time we apply the input, we need to switch the input between two voltage levels. So input is to be connected to 0 volts, 5 volts, 0 volts, 5 volts. When you change the inputs, so the input will be maybe made with some sort of electronic switch like MOSFET or something which has some capacitance, which requires some time to charge and discharge. इसलिए it requires some time to change the input here. So to overcome this disadvantage, we go for current switched R to R type ADC, sorry DAC, where we will be switching for both what we call logic 0 and logic 1 between same voltages, but current will be switched. That is same voltages will be 0. That is we will show it with the help of the next figure now. See here, what is this node voltage? 0 volts. By virtual short, this is also 0 volts. So this node voltage is also 0 volts. So here you observe, first it will work or not, मैं तो explain करता हूँ. Switch can be moved to this position or this position. In any case, I am say when a particular bit is 1, I will connect here. Particular bit is 0, I will connect here. But both the cases, the voltage available will be 0 volts only, na? So in any case, this will be, I mean, you connect to the top one or bottom one, both the cases you get 0 volts only. But the current coming here, if you see, R 2R parallel with 2R is R series with R, 2R parallel with 2R, R series with R, 2R parallel with 2R is R series with R, 2R parallel with 2R is R. Why it is parallel? Because they are connected to same voltages here and here. Whether it is connected to here or here, it is ground only, na? So the current I input is VR by R. Okay. I in or I whatever may be. Okay. Now this current, this total is 2R, this is 2R. So current divides into two parts, I by 2, I by 2. So this will also divide into I by 4, I by 4, I by 8, I by 8, I by 16 and I by 16. This is what happens, right? So when the switch is connected to here and here, whatever may be, so the current will divide accordingly. Now listen carefully. So it is giving some current I naught. Op amp में कोई current नहीं चलेगा. This I naught will come here, and what is the drop you get? Minus I naught into RF. Now what is I naught? If a particular bit, say particular bit 3 is equal to 1, what is the current you will get? The bit 3 1 hai to switch will be here and it will give you I by 2 here in this part. Okay. So bit 3 will give you I by 2. So bit 3 1 hai to it will give you I by 2, nahi hai to 0. Bit 2 will give you I by 4. Bit 1 will give you I by 8. Bit 0 will give me I by 16. It is depending on the particular bit, you may get by 2, by 4, by 8, by 16. This is I naught. So V naught is equal to, what is that? Minus, you take I common, bit 3 by 2, bit 2 by 4, bit 1 by 8, bit 0 by 16, okay, into RF. But what is I? It is minus, what is I? What is I is VR by R into RF. You take here LCM. What is LCM? You get 16, 8B3 plus 4B2 plus 2B1 plus B0. Right. Now it is, you take, just multiply with 15, divide with 15, same story. VR by R, RF by 16 into, this is the decimal equivalent of the input, and this part I will write it as V reference by 2 to the power of 4 minus 1 into decimal equivalent. That gives you, so I am able to achieve the same resolution into decimal equivalent without switching between two different voltages. Here I am switching between two different same voltage levels, but current is switched. So this circuit is called current switched R to R type DAC. Right, that is about your current switched R to R type DAC. So that will finish your ADC and DAC theoretical part. Now we will do the problems based on this. Before going to problems, I feel we can do one thing. Right, so please try this. Read this. So please try. This is not a difficult question. Here he want this current I. This is the VR, V in or VR, whatever maybe, which is equal to 10 volts. 20 seconds more. Time up. Here, firstly, what is the current we are getting here is, let's take I in. So you get I in by 2 here, I in by 2 here. You get I in upon 4 here, I in upon 4 here. You get I in by 8 and I in by 8. This will be I in by 16. So this will be I in by 16. So what is your I in? V in by R, that is 10K upon, 10 upon 10K, 1 milliampere. So what is the small I? 1 milliampere by 16, 1 by 16. Okay. $62.5 microamperes. This is the first question. Same model, this is nothing but current switched R to R type ADC. The same model, one more question is given. So give a try. Here we already know that this is I in by 4 and this is I in by 16 and I in is equal to 1 milliamp. We calculated this part already. Now you need to find the output voltage. So give a try. Just find V naught. R equal to how much? 10 kilo ohm. Okay. Here already you know this part. So what is this current? I in by 4 plus I in by 16. That will give you 5 I in by 16. This current is 0. This will be 5 times I in by 16. Current enters from positive to least from negative. What is your V naught? 5 I in by 60 into 10 K. K and that will go 1 milliampere. So 50 by 16. So the answer is the 3.125. You take current enters, so it is minus to I. I in is 1 milliampere, 1 and K will milliampere and K will go. Output is minus 3.125. Okay. Next. So let's try this question. This is also a question based on R2R type of DAC wala question hai. So give a try. So it is a R2, sorry, weighted resistor type of DAC, 4-bit weighted resistor type DAC, 0 and 1 corresponding to 0 volts and 5 volts respectively. Op-amp is ideal, but all the resistances and the 5 volt inputs have a tolerance of 10%. Expected may plus or minus 10%, it can vary. The specification of the round it to nearest multiple of 5 for the tolerance. For tolerance ka nearest tolerance of the total DAC. Output may how much variation you can expect is the question. Okay. See here. What is your V naught minus R by R into D3, R by 2R into D2, R by 4R into D1, R by 8R into D naught. This is the output. So I write it in the next page. What is your V naught expected is minus R by R into, don't cancel R. Okay, here the tolerance plays an important role. And you take 8 times VR into V3. This is D3 can be written as the voltage you apply. VR is here 5 volts. Okay. VR is the voltage you apply when the particular bit is equal to 1. That is here 5. So 4 times VR V2. This is already the derivation we have done only. So I can say it is minus VR into V3 by 2, VR into V2 by 4, VR into V1 by 8, VR into V0 by 16. So minus R by R, you take VR common, 16 common, 8 V3 plus 4 V2 plus 2 V1 plus V0. So minus VR by 16 into R by R into decimal equivalent of the number is the output you get. Directly I can write it, but just like a revision I have again derived it the same what we have discussed in the R2R, sorry, weighted register type DAC. Now this is expected V, but what is your V naught? Measured. आपको क्या मिला? Measured can be here, आप जो expect कर रहे हैं ना 5 volts, that will be having plus or minus 10% tolerance. Let me take first plus 10% tolerance. So this will be VR is expected that you got is 1.1 VR. R is expected, but what you got it is 1.1 R. So what is R plus or minus 10% is 0.9 R to 1.1 R. That is the meaning of the tolerance. So here, why? If you take here 16 is a number, there is no changes you can apply. But here, so voltage is also increased by 10%. For example, resistance is also increased by 10%. What about the denominator wala resistor? Denominator wala resistor means the resistor we are using here, the resistor we are using here, and here we are speaking. If all the resistors we are using the other end, worst case, what is the resistance? What is the tolerance you can get? It is highest tolerance we want to measure. Highest possible tolerance will occur. If this is also 1.1 R, it will cancel. So this must be 0.9 R. In this case, you get the maximum possible tolerance, that is 1.1 into 1.1 by maximum possible deviation by VR by 16 into R by R into D. That is nothing but expected into 1.34. That is your measured. What is the error percentage formula? Measured value minus expected value by measured value into 100%. So that will give me 1.34 VE minus VE by measured minus expected by expected na? Into 100%. That will give you yes, perfect. So that will give you 34%. It will round off to 35%. He asked the round off to the nearest possible integer, that is 35, nearest multiple of 5%. You can also do in a different way, but that will give you less answer. So definitely this is the right answer. So you can also do another possible way is, or you can also say Vm equal to, instead of 1.1, take numerator equal to 0.9 and denominator equal to 1.1. That is also possible. So that is minus 0.9 VR by 16, 0.9 R by 1.1 R you should take. In dono mein whatever the maximum, we should take that one only. So here you get 0.9 into 0.9 by 1.1 into VE. So what is the answer? 0.73. Here what is the error percentage? Okay, around 27% you will get. Okay, so definitely this is the answer. Okay, maybe minus 27. Forget about plus and minus. So plus or minus 35 is the what is the round of the nearest integer of 5. So the next question. Okay, so try this question. 10 seconds more. 14. The last lecture we will be discussing is tomorrow. Okay. So student has made a 3-bit binary down counter connected. Binary down counter may expected is what? 7, 6, 5, 4, 3, 2, 1, 0. So the counter output he has connected to R2 or DAC. The output should be decreasing 7, 6, 5, 4, 3, 2, 1. So staircase waveform जैसा होना चाहिए. But the output achieved is something different. So what is your expected output here? What is the expected output? Expected is Q2, Q1, Q0 must be all zeros, all ones, 110, 101, 100, 011, 00, sorry, 010, 001, 000. But measured kya? What you got it is, you see this is 7 first, then it got 3, 5, 7, 3, 5, 1, 6, 2, 4. Okay. So you will be getting what you got is 7, 6, 6, 9, 3, 7, 3, 5, 1, 6, 2, 4, 0. This is what you measured. Okay. 7, 3, 5, 6, 2, 4, 0. 7, 3, 5, 7, 3, 5, 1, 6, 2, 4, 0. 6, 2, 4, 0. So is there any relation between these two? If you observe, yes, there is a relation that is called bit reversal. That is, you see this particular pattern and this particular pattern are mirror image to each other. So here this particular bits are reverse हो गया, ये दोनों उल्टा हो गया भाई, फ्लिप हो गया. Q2 का जगह पे Q0, Q0 का जगह पे Q2 कनेक्ट हो गया. ठीक है. So this here Q0 is connected, here Q2 is connected, that is reverse पे connect किया. So the connections from the counter to DAC are not connected properly is the right answer. Next question. The similar model, one more question. Try. Right. Time out. So here Q2, Q1, Q0 are connected to D3, D1, D0, and D2 is left 0 to the up counter. So here the up counter inputs are, you start with all zeros. So what is the output? You will be getting it 0, 1, 2, 3, 8, 9, 10, 11. So it is 0, 1, 2, 3, 8, 9. It will be like this 0, 1, 2, 3. It will increase 8, 9, 10, 11. Again it becomes 0, 1, 2, 3. So this kind of pattern you will get. Normally, if it is a normally connected, a 4-bit is connected to 4-bit or 3-bit is directly connected to 3-bit, you get a staircase waveform. But in this case, what is the output you will be getting? It is, this is not the case. This is the case approximately. Okay. Right. So that is about your output when this is the connection. So let's move for the next question. So try this question. You have a 10-bit ADC with a full-scale output voltage of 10.24 is designed to have plus or minus half LSB accuracy. If the ADC is calibrated at 25 degrees and operated at the temperature of 0 to 50 degrees, the maximum temperature coefficient of the ADC. It is based on what we call ADC specifications. Okay, please try. Tomorrow we discuss ADC, but specifications more or less it is similar. You can answer this question. Right. So you have a 10-bit ADC with a full scale output of, firstly, what is your V reference? What is the resolution? 10.24 by 2 to the power of 10 minus 1, approximately 10 millivolts. Is designed to have plus or minus half LSB. Plus or minus half LSB is how much? Plus or minus 5 millivolts. Right. If the ADC is calibrated at 25 degrees, so I have made it at 25 degrees calibrated, and I am operating with 0 to 50 degrees. Right. So the operating temperature is 0 to 50. So maximum temperature coefficient of the ADC. So it is okay if my output is varying plus or minus half LSB, that is plus or minus 5 millivolts, that it can vary. So this gap can give me plus or minus 5 millivolts. This gap can give me plus or minus 5 millivolts. So what is that gap? This 25 degrees temperature variation can give me up to 5 millivolts variation. So 25 degrees may my output can vary 5 millivolts, no problem. 1 degree, how much it can vary maximum? 5 by 25. That will give you into 10 power minus 3. That will give you 200 microvolts per second. Okay, per degree. Okay, so plus or minus 200 microvolts per 1 degree it is allowed. For 25 degrees, it is, what is that? 5 millivolts. For 1 degree, how much is the question? So this is the last question of today's class. Okay, tomorrow we discuss the counters type ADC. Okay, please try. You have 8-bit DAC is implemented using two 4-bit DACs. You need to find the value of R for this. Maybe it requires a little more time. You can try. So give a try. So last 20 seconds. Time up. Time up. First read the question. It shows the implementation of 8-bit DAC using two identical 4-bit DACs, equal reference voltages. So equal resolution also. Assume that B0 represents the LSB, B7 represents the MSB, and the op amp is ideal. To obtain the correct analog values corresponding to an 8-bit DAC at the output V0, the value of R will be simple, very simple. Here normally it is taken as B0 only, because 4-bit DAC means this is B0, but you should read it as B4. Means what is the difference between B0 and B4? 2 power 4, 2 power 0, 2 power 1, 2 power 2, 2 power 3. This should be 2 power 4, this should be 2 power 7, but normally it will take it as 2 power 0 and 2 power 3 only. So it should be multiplied by 2 power 4. So the multiplication factor is 2 power 4. 8k by R must be 2 power 4. R must be 8k by 16, that is 0.5k. Maybe some people are not happy with this, so let me explain in a better way. So what is your V0? V0 is equal to resolution into decimal equivalent is my requirement. Resolution into 2 to the power of 7 B7, 2 to the power of 4 B4, 2 to the power of 3 B3 plus 2 to the power of 0 B0 is what I am expecting as an 8-bit DAC. But what you are getting here is minus को छोड़ दो, 8k by 8k into what is that? Sorry, 8k by R into V02 plus 8k by 8k into V01. So this will be giving you some x into V02 plus V0. Okay, here R is resolution, because here in the question also there is one R, that is resistance. Okay, don't confuse. So yahi tak theek hai. This I am replacing with x. Okay, my required condition is the x must be how much, we will see. You can divide this into R into 2 to the power of 4 into 2 power 3 B7 plus 2 power 0 B4 plus, okay, this is R into 2 to the power of 3 B3 and so on, 2 power 0 into B0. I just made some mathematically. I take this R up to this part and R up to this part. I take 2 to the power of 4 common. Why I am doing that, I will tell you. Firstly, for the 4-bit DAC, what is V01? What is the V01 of the first 4-bit DAC? V01 is 2 to the power resolution into decimal equivalent, 2 power 3 B3, 2 to the power of 0 into V0. Right. What about V02? It is same, resolution into 2 to the power of 3 into B7, 2 to the power of 0 into B4. We have applied B4 to B7, but its original working nature will not change as you applied B4. I should do the necessary change in the B4 such that it will do my necessary requirement. So you understand here. Okay. So this is your V01. Yes or no? So what is your required condition is 2 to the power of 4 into this what is there, R into 2 to the power of B7 to 2 to the power of B0 is V02 plus what is this, R into 2 to the power of this to this is, I am writing it as V01. Okay, so this is my required and this is what I am obtaining. You just check what is the value of x required comparing to this. I got this equation from the, I mean, this is my necessary, this is the expected, this is the measured from the circuit. From the expected equation is this one. I took what we call, from the expected equation, I have taken that what we call this 2 power 4 common in the first part, then 2 power 3 b7 to 2 power 0 b4. Second part I just multiplied. This is nothing but my v naught 1. This is nothing but my v naught 2 into 2 to the power of 4. So figure will tell me the equation output is 8k by r into v naught 2 plus 8k by 8k into v naught 1. So this 8k by r is my x. My x must be equal to how much? Forget about minus 2 to the power of 4 to satisfy that condition, that is 8k by r. So what is the value of r? That is resistance 0.5. This is the output resolution. It remains the same as the original individual resolution of the 8-bit DAC and 4-bit DAC. In this case will be same, but what changes is the full scale output will change according to the case circuit you have taken, but resolution remains the same. So that is about your question. Without doing all this, I have directly done. Chalo. So that will finish the DAC part today. Tomorrow we will start with analog to digital converters and we will do its particular corresponding problems also, counter type DAC and all. So Unacademy price is going to rise by 30%. Now if you take the subscription, you have an opportunity. You can save up to 30%. All you need to do is use the code Shankar10. You will get the maximum possible discount up to 30%. You can say, you can join my Telegram channel also. It is the same. I will share the notes after the next class. Total subject ka notes I will share together. Okay, मेरा टेलीग्राम चैनल पे ज्वाइन करो and you can subscribe to Unacademy. You, your junior, anybody want to take the subscription. Whenever you have the plan, use my code Shankar10. So these are our toppers this year from 22 ESC examination of electrical and DC guys. Okay, so the mission IRMS batch is also started guys. If you want to take the subscription, you can start your journey with Unacademy. You can use my code Shankar10 to get the combo of GATE and UPSC GS. Okay, so the last AMT examination is happening this Sunday. Don't miss this opportunity. This is compulsory because before going for the final exam, this is the only opportunity you have to write the mock test. Write it, check yourself, compare yourself with others, and then rectify your mistakes and go for the final exam. All the best. So tomorrow we will meet for the data converters last topic. Okay. Thank you. Tomorrow we will discuss ADC and finish this digital in 20 hours. Okay, irrespective of your strength, I have made my promise and I obeyed that. Okay, all the very best guys. Thank you.